Okay, so we continue our discussion on central orbit. Now, in central orbit, we in the last two classes we have discussed equivalent one dimensional problem, and we took up the special case of inverse square force field, but and then we moved on to the orbital sciences, like we derived equations for elliptical orbit, circular orbit, derived condition for elliptical orbit and circular orbit. We will continue with that, but prior to that we will spend few minutes on the equivalent one dimensional problem once again, because I forgot to mention, I forgot to focus on certain features of this problem. Now, if you recall, this was my, let us say this is my r axis and this is my energy axis. Okay. Now, what we could do, or what we did actually, let us say this is, and for V effective this is given. Okay, so I will write little lower. V effective is V of r plus L square by 2m r square, right. So, this is the functional form for this particular effective potential. Now, L square by 2m r square, I mean L square by 2m, as we have discussed, it is a positive definite quantity. So, we will always get a potential which will look like this. Okay. So, this dependence is 1 over r square dependence. Now, we have let us say we have a VR, we discussed the case 1, VR is equal to minus k by r. So, this is an attractive inverse square force law, that means the potential force is 1 over k by r square. So, the potential is minus k by r, and this the potential looks something like this, and overall the effective potential is something like this. So, we have discussed this case in details. Now, what happens that if instead of having V of r as minus k by r, if we have V of r is equal to k by r, where k is greater than 0. In this case, it will also, I mean, instead of being in the negative side, k of r or V of r will always remain in the positive side, but it will fall slowly like this. So, this is k by r and this one is minus k by r, right. So, in this case the effective potential, which is represented by this dotted line, will look something like this. Okay. So, V effective will be this in case when we have a inverse negative attractive potential, and V effective will be this when we will have an when we will have a repulsive potential, this will be the shape of V effective. And you can immediately see from the shape of this potential that bound states are not possible for this particular potential, because there is no such dip, there is no such minimum in this potential. Okay. So, only possible motion under this dotted line, or if the potential effective potential is something like a dotted line, is a scattered orbit, which could be a and it cannot even be a parabola, because for parabola the condition is energy, total energy has to be at E equal to 0, and this is the condition for parabola. Okay. So, if we have a repulsive inverse square force field which will give this potential, we can only have scattering for energies greater than 0 and with hyperbolic orbit. So, here we have scattering for particle energy E greater than 0 and hyperbolic orbit. Okay. So, this is one case. Let us discuss the case if we have a potential which is given by V r is equal to minus k by r square. So, if the force is given by inverse cubed, I mean if force is attractive with inverse cube of r, then this will be the form of the potential. Now, as always, your centrifugal term will be this one, and your attractor, this potential V of r, the plot will look something like this. Okay. Now, in the hypothetical case when L square by 2m is equal to k, if this particular condition is satisfied, then two sides at each point will cancel out exactly, and it will look like as if the net or what I mean is the effective potential will be a flat line. Okay. If L square by m twice m is greater than k, then the effective potential will be something like this, and if L square by m twice m is less than k, okay. So, this lower part is dominant, then my effective potential will be something like this, right. So, this is another case. The third case is when we have V of r to be equal to minus k by r cubed, right. Okay. So, what happens, okay, before that, what happens if we have k by r square with k greater than 0 instead of having a repulsive attractive potential, if we have a repulsive potential. So, the potential will always be on the upper part of this diagram. So, this is my r and this is my v diagram, and once again there will be only possible motion will be scattering motion with some orbit, but this time it will not be an hyperbolic orbit, because I mean it might or might not be an hyperbolic orbit, we do not know a priori once we because this is not an inverse square potential, right. Now, for k by r cubed, now we have slightly different situation. This is my L square by twice m r square term, which falls off with 1 over r square, and for if k is greater than 0, then we have a term which falls with 1 over r cubed in the negative direction. Now, if this is the case, then my effective potential will look something like this one. So, you see in this picture, this one falls faster. So, at lower side of r this will be dominated, and for higher side of r this will be dominating, I mean the upper part will be dominating. So, the effective potential will look something like this. Okay. So, in this case we can have a bound motion, this is possible, but the bound motion will be one of the lower bound will be the origin where there is a discontinuity in the force. Okay. So, we can have a bound motion in this region, or we can have a scattering in this region, and for energies slightly higher than this we will have nothing. The particle which comes with an energy higher than this threshold, this particular threshold, it cannot feel the presence of this potential. So, if the energy is somewhere here, this particle which comes with this particular energy E, which is greater than this threshold, will not experience the presence of this potential at all. For energies which is below this limit, they can have either a scattered motion if they are coming from this side, or they can have a bound motion in this region, right. And in this case, for bound motion, the particle will pass through the force center during its path. Okay. So, this is case number 3. Also, if we have a positive sign here, if we have a pure repulsive potential, once again the net potential will be in this side in the upper part, and there is always scattering. Now, the fourth one which we are going to discuss is slightly different. We will take half k r square. This is the familiar Hooke's law, which produces simple harmonic oscillation, right. Now, here here in this particular case, we first draw this half k r square. We know that it is a parabola, something like this, right. Now, this effective potential, depending on which dimension the motion takes place, the shape of effective potential will change. If we have 1D motion, then L is equal to 0. So, V effective will be equal to V of R. This. So, if we have r square equal to x square for say, so we will have only one possible potential, only one contribution in the effective potential, because L is equal to 0, and my effective potential and my actual potential will coincide. Okay. But if we have, let us say, 2D or 2D motion or any other dimension of motion, 2D or 3D motion, where R is in general represented by x I cap plus y j cap, so and z k cap, 2D or actually let us call it 3D motion. In this case, we will, so when the motion is not confined on a straight line, we will have an L which is not equal to 0. Once again we have this term back, and my effective potential will look something like this. Okay. Same for any higher orders of R. If we have, instead of Hooke's law, if we have k r to the power 5 or something, we can always have a potential, in principle, which looks something like this. So, we have a bound state where origin is also not accessible, because at origin this potential well at r equal to 0 goes to infinity. Also, the higher values of r is also not accessible, because this side also it goes to infinity. The only possible motion in this potential is the bound motion between these two levels for this energy, or between these two levels for this energy. So, either between R1 and R2, R3 and R4. So, if E is energy is equal to E1, then the motion is bound between R1 and R2, and if E is equal to E2, then the motion is bound between R3 and R4, right. So, this is how the effective potentials for different problems or different sets of potential, different sets of force law, different types of force law looks like. So, I wanted to give you a very brief description of this. And now, if we go back to the last problem of our problem set 1, I am not going to solve it for you, because it's something that you need to figure it out yourself. It is not a problem exactly. Okay, this particular problem, it is not a problem exactly, but it is kind of a quantitative description of what is going to happen. If we have this type of potential where k is positive definite and k prime might or might not be greater than 0, what will be the different shapes? First of all, we have to, for part 1, we have to determine the potential function. I should write effective potential V effective. So, we have to draw the different types of potential function, and we have to put energies which is higher, equal to or less than equal to 0, and then we have to see whether we will have bound motion, unbound motion possible in this case. So, it is a example that you should, or it is an exercise that you should try yourself. So, I am just closing it for now. Let us move on with our discussion on orbital motion. So, I have divided this discussion on central force into two parts. One where one is up to the description of effective potential, and the second part is when we are discussing the orbits, because orbit is something that you do not find in typical textbooks. It has not been discussed. I would suggest the textbook of Raychaudhuri and Maiti, which is listed in the reference book list. That book has a very nice description, and also you will find it, some of it will be definitely available on internet. Also there are a certain group of textbooks which are classical mechanics or mechanics for engineering students, in which the topic will be covered. But for now, for you, for physics students, I think Raychaudhuri and Maiti is a very good book for this. Okay. So, let us continue our discussion. Now, in the last class what we did was we figured out what are the conditions for circular and elliptic orbit. So, let us say this is our earth with radius r0. So, from this position something is fired, I mean an object is fired at an angle alpha with the horizontal direction. Depending on its velocity, whether the velocity v is greater than or v falls in the range of VE by root 2 or in the range of VE by root 2 to VE, it will have for an bound or circulating orbit. So, we have seen that if this is the scenario, then we have a bound orbit. Okay. So, the orbit will look something like this. Okay. And if this is the case, then we will have a circulating orbit, right. Okay. So, this is an orbit which is, this is an elliptical orbit which is typical for a satellite, and the red marked one which is typical for a satellite. So, this will give us a satellite, and this will, the orbit which is closed here, or which is not a circulating orbit, which will come back to the earth's surface once again, is the orbit of a ballistic missile. Okay. So, we have discussed this already, and we have found out the, okay. So, this ranges is an outcome of solution of solution of some equation. Also, we have seen that if V is equal to VE by root 2 and alpha, the launch angle, is equal to pi by 2, then we will have a circular orbit. So, this is a special case that we have seen already. Now, let us try to focus on this particular case. Satellite we have seen. So, for satellite we will come back to this later. For right now, let us focus on the ballistic missile and try to see if we can get an expression for its range. Now, what happens is, okay, we can modify this picture slightly. So, this, please remember, this remains the force center. Okay. So, we can draw a line which goes through the farthest point or the perigee distance of a ballistic missile. Okay. From this line, we can draw a angle, call it phi 0, okay, and any position, any point on this which is measured once again with reference to this particular axis. So, basically we have, okay, let us call this theta, this angle between this two line, this line and this line theta, and let us call this angle to be equal to phi. Okay. So, basically we have two reference angles, one which is measured with respect to the vertical direction at the point of its launch, that is called phi, and another is the angle theta which is measured along the apice line. Okay. So, the line which joins the force center and the perigee position is definitely the apice line, and according to this line the equation of the orbit will be, as we have already seen, L by r is equal to 1 minus epsilon cos theta. Why 1 minus? Please recall that if this is your ellipse, okay, and it is going in this direction, if this focus is your force center, then the equation was L by r is equal to 1 plus epsilon cos theta. But if this is your force center, then your equation was L by r is equal to 1 minus epsilon cos theta. So, in this case our force center, if you try to just rotate this picture and fit in here, you will get the, you will see that this equation is the valid equation. So, this is my equation, and we see that theta is equal to nothing but phi minus phi 0, right. So, we can write this as cos phi minus phi 0. Why phi and phi 0? Because these are the angles which are easy to measure, that is something we know a priori. Theta is something that we have to construct. We first know we need to draw this line and then we need to construct theta, right. So, it is just a pure mathematical manipulation. Now, what happens is we take this equation, or we can just, yeah, we take this equation and we can start putting the values of L and see what happens. So, 1 minus epsilon cos phi minus phi 0 is equal to L by r. Please remember L is equal to L square by m k r. Now, we substitute the values for L and k. L is equal to m v r 0 sin alpha, and k is equal to m v square r 0 by 2. This comes from the straightforward calculation of angular momentum, and this comes from the escape velocity definition. Okay. So, this is how we define the escape velocity. Once we put these values in here in this expression and simplify, we see that the expression becomes 2 c square r 0 sin alpha divided by r. Okay. So, I am not showing this calculation, but you can do it, it is pretty trivial, pretty straightforward. Okay. Now, if we use the initial condition at t equal to 0, okay, at time when the projectile shot was fired, r is equal to r 0 and phi is equal to 0, then that gives us, and if we put it into this equation, this gives us cos phi 0 is equal to 1 minus 2 c square sin square alpha by epsilon. Okay. Once again I am showing you, I am not showing you the details of calculation, but it is pretty simple. You get this expression, then you put these two boundary condition, you put r equal to r 0 and theta is equal to 0, and you immediately see this is the expression. Now, if this is the expression, then okay, if this is the expression, then we can write r to be equal to r 0 1 minus epsilon cos phi 0 divided by 1 minus epsilon cos phi minus phi 0. Why this is? Because if you if you look into this expression, okay. So now use this in so this was my starting point of starting equation, okay. Now you have to substitute this into this equation and you will get this relation at the end, right. So now if we what is our aim? We want to see how far this projectile actually travels, okay. So we want to have an estimate of this length, right. So in order to have an estimate of this length, we have to look for the extremum of angle. So if I know this angular displacement, we just have to multiply. If we know this angular displacement here, we just have to multiply it with this r0 and this will give us the total length travelled along the earth's surface, right. Okay. So we get this particular expression and we put r equal to r0 here. So if I put r equal to r0 here, I see that 1 minus epsilon cos phi minus phi 0 is equal to 1 minus epsilon cos phi 0. So that means cos phi minus phi 0 is equal to cos phi 0, and this could be true if phi 0 is equal to 0 or 2 phi 0, or phi is equal to 0 or 2 phi 0, right. Now phi is equal to 0, if you look carefully, phi is equal to 0 is this particular position, okay, where from so that is the point where the projectile was launched. So this angle has to be equal to 2 phi 0, okay. So we need to have two solutions for this equation, or 2 points where the projectile touches earth. This is the initial point. So this is the point of our interest. Now if we accept this as our answer, then the range of ballistic missile equal to which we can denote by r is equal to 2 r0 phi 0, right. Okay. So this is our relation, and phi 0 is, we can get the value of phi 0 by examining this particular expression. Cos phi 0 is equal to 1 minus c square sin square alpha by epsilon. Epsilon also we have seen that this can be written in terms of this initial parameter. So once we know the initial launching condition, we know alpha and we know c, and in principle that means we also know epsilon, we can immediately calculate phi 0, and from phi 0 we can just calculate the range as 2r times phi 0. Okay. So this is that's it for today. So tomorrow's class we will take up problems and we will solve many problems related to this orbit transfer, not orbit transfer, that's one thing we have not covered. So we will talk about orbital motions, escape velocity and other topics. Thank you.